All right. So today we are going to continue what you can consider a series of 3 lectures on controllers that are slightly more complicated than what we have seen before. So let me remind you what we did last week. What we considered last week was the case when we couldn't depend on having X available to us. So we said that our classical controller, the controller that we have been studying this whole time, that looks something like U equals to kx, right? Maybe minus kx. We cannot do it anymore if we don't have x. And it is quite normal not to have x, because x is information that you have to get from somewhere. In practical systems, we only measure some components of x. All right, fair enough. Seems reasonable. Our answer was to invent a system that we called observer. It is basically a system which estimates x. It produces good estimates of what x currently is. And those estimates, as time goes to forward, right, get better and better. So we had a problem, we solved it by introducing observer. And somehow this controller plus observer pair works well. They don't work separately anymore. They work together. Okay, good. So today, this idea of this like more complicated system, we'll try to make it more general. We'll try to understand it and see more examples of the same behavior with controllers. All right, let's try to do it. So before, I think it would be good for us to simply sort of get some abstractions that somehow make it a little bit more clear what is going on. So one very useful, but maybe a little bit not obvious abstraction is a system, all right? So we can think about a system as being characterized by how it relates inputs to outputs, right? So how the input and outputs are being related to each other. For example, a controller that we are familiar with, like U equals to kx, is a system. It relates its input, which is x, to its output, which is U, right? So that is example of a system. Another one is a plant. Plant is, for us, usually this whole thing. X dot equals to ax plus bu, y equals to cx. That together we can call plant. This is also a system. This one relates its input u to its output y. Okay. And finally, also plant. So dynamical system we want to control. It can be described as output y in Laplace variables equals to transfer function times x in Laplace variables. All right. So that is the examples. So let me also clear a little bit the terminology. The word plant, we haven't been using it a lot, but the main reason is because we here somehow think about control theory from the perspectives of robotics, right? So for me, the tendency would be to say, this is a robot. This is a description of your robot, right? You want to control a robot? This is a model of the robot. You want to control a robot? This is a model of a robot. That is my tendency to sort of tie it down to what you are actually working with. But control theory is, of course, more general than robotics, right? It is widely used in aviation, where this would be, for example, airplane, right? Or maybe a subsystem of your airplane. But airplane itself is a good example. Okay. But even before that, control theory is widely used in chemical processing. And that is where you get the word plant. So you can think of a chemical plant as being described by linear equations. And then you call the system itself plant. Yeah, that is the idea. The word plant is extremely useful because the word system is being used so often for so many different aspects that we need more words. So the word plant is being used by roboticists as well as other general practitioners. So it's good to remember. Word plant basically refers to a dynamical system you want to control. Usually you can think of it as a dichotomy between plant and controller. Plant is what is given to you by engineering problem. Controller is what you design to control this plant. Okay. All right. But all three of those are systems, right? Controller is a system, plant is a system. Okay, good. Now, in this lecture, we are going to consider only linear systems. So other nonlinear systems, I mean, depends on how you define a system, but of course, right? You can easily define a nonlinear system. For example, a pendulum, you can describe it as a nonlinear system. Okay. But we, in this lecture, concentrate on linear systems only. Now, for some systems, it is true that the relation between the input and the output does not depend on time, right? So this relation stay exactly the same as time goes on, right? So such systems we can call static. Such systems we can call static. This definition is a little bit how should I put it? You have to be careful because Laplace systems, for example, do not include explicit time. So somehow when I talk about this, I imply that the system is presented either as an ODE or as a state space form, right? So like with those definitions, you always have to be careful. But yeah, the relation between input and output does not depend on time. Then it is static. So let's look at a couple examples. So this controller, u equals to kx, is static. Doesn't matter what time of the day it is, doesn't matter what happens, it is always going to be input gets multiplied by a matrix, you get output. Same matrix, any time, any, like, always the same. All right. Another one, gain function. Gain function is basically just a fancy way to say multiply by a constant, right? Is also the same. Because, how can we see that it is the same? Well, visually it looks like it doesn't depend on time, because what happens is input gets multiplied by 10. 10 does not depend on time. But of course, it is also a Laplace transform. So time would not appear in Laplace transform. If you remember, Laplace transform is an integral over time, where we get the time out by integrating it. We integrate it out, but we get a new variable. So we have to be careful. But in time domain, this system would look like this. And this you can clearly see is also independent of time. Remember, when I say independent of time, what I mean is that the relation is independent on time, not the signals. Signals can depend on time. The relation between the input and output. does not depend on time. A relation is always 10 times bigger. All right. Static system. As you can imagine, static systems are important because they're so simple, like completely predictable, just a linear equation of some kind. If you have any questions, please interrupt me, ask. Okay. So that is not the only way those things work. So for example, we can have linear systems where relation between input and output depends on time. Okay. So far we were talking about systems where those things independent on time. Can be the opposite. They can depend on time. Those systems we will call dynamic. So let's consider how this works. Oh, one example is plant, our state space plant, right? Why does the relation between U and so remember, this is input, this is output. Why does the relation between input and output depend on time? Well, because as time goes on, X changes, right? X changes. So you can imagine if in the beginning X is 0, let's say in the beginning X is 0, well, then the output is 0, regardless of what input you have. Later, let's say under the influence of U, X slowly starts to approach 1. It goes towards 1. Well, as it going towards 1, U goes to C, right? C times 1. If C is a vector, or let's say C is just a scalar, so it will go towards the value C, okay? But it won't reach the value C for a while. So for a while, the Y would just be reaching the value C, where X is reaching the value 1. At some point, let's say X approached value 1 exactly, so it's exactly 1. Then Y becomes exactly C. Right? You can see that U can be constant, right? It can be constant the whole time, but Y would change with time because edge X changes with time. So you can see a relation between them depends on time. You cannot say, oh, Y is always 5 times bigger than U. That's not true. The relations between them cannot be described in this form. You have to describe them as a function of time. Okay. Now, another example is a plant in Laplace domain. Here's input, here's output. And here you have your transfer function. Here, you need to be careful. Time does not appear anywhere in this equation. But if you transform it back into an ODE, what you would have is y double dot plus 2y dot plus 7y is equal to x. Mm. And this would give you a equation where the relation between x and y would indeed depend on time, right? Given a certain because y itself would depend on time, right? And x, even if it is constant, is not going to give you a constant y. So the relation between those two would depend on time. And exact same situation here, right? This is the same kind of like general idea, just written out in ODE form. Okay. So two different situations: dynamical system, statical system. All right. In fact, for dynamical system, we could say that the output depends on the entire history of inputs, not only on the current input. Because you can imagine if, for example, here, x behaves like this. It is equal to, let's say, 0 when t is less than 5. And then it is equal to 1 when t is bigger or equal to 5. Well, the fact that the first 5 seconds x was equal to 0 will affect what y will be for the rest of the trajectory. So you cannot just look at y or at x currently to determine y. It is not sufficient to just know the time and just know current value of x. You have to know the entire history of x and current time in order to evaluate what y will be. So that is a big difference between dynamical systems and statical systems. Okay. This, by the way, is not a disadvantage necessarily. This means that dynamical system can take into account everything that happened. It stores this information. That is not necessarily a bad thing. Okay. Now, the two systems can be thought of in this way. Static systems form algebraic linear equations, right? Algebraic linear equations. Whereas dynamic systems form differential equations, right? You can think of them this way. Of course, we represent them in Laplace form as well as state space form, ODE form, but we can always transform them into ODEs, right? Static systems kind of naturally look like linear equations, but even if they don't, for some reason, we can always transform them into linear equations. Okay. Now, what is interesting is that dynamical systems have additional property. They have state, right? They have state. You can think of state as some kind of internal variable which itself changes with time, right? Affecting the relation between the input and the output. So statical system clearly does not have any variable like that because the relation between the input and the output are not affected. But dynamical system does have a variable like that. So dynamical system, we can think of it as, unlike static system, having some internal variables that do some work inside the system. Okay. Now, our controller plus observer that we studied previously is also a dynamical system. The input to this dynamical system is a measurement y. And the output of the system is control signal u, right? The state of the system is x hat, okay? So let's just look at this system. So I have x hat dot equals to a x hat. This is a Leuenberger observer. Like all of this is a Leuenberger observer. Last lecture. So x hat dot equals to a x hat plus bu plus L, that is observer gain. Remember, observer gain. Right? It multiplies the difference between actual output and observed output. Okay. And here is your input, right? One second. So here is your input y, right? Input y. minus c x hat. And here's your output here. Like this below, this whole thing is a controller. This is your normal controller like LQR or whatever you have, proportional controller. So here's your output. And you can see it depends on the state minus k x hat. Okay. Now, if you look at this closely, what you would find is that it resembles very much normal plant, right? Normal LTI. X dot equals to some matrix, A minus LC X hat plus BU. Okay. This is not like completely usual for us to see U both here and here, but why not? If you don't like seeing U here, you can always replace it with minus K X hat. So it would be A minus BK plus minus LC X hat, all right, plus Ly U equals to minus kx hat. Okay. So this is very much the same as what we usually see in our LTIs. Okay. So we can think of this combination as a dynamic controller, right? We could keep separating them. We could say, okay, this is observer, and this is controller, like two different entities. And that is perfectly valid. Often enough, it is what we want to do. And separation principle, you remember last lecture, separation principle allows us to design those separately and still get our performance. We still get our optimality in terms of eigenvalues. We get our eigenvalues. Let's say it this way. We have our eigenvalues and we have stability. So somehow we could separate them, but we don't have to, right? Together, all of this forms one entity, and it is a dynamic controller. Okay. Now, this way of thinking points out that this controller has internal state, which would change with time. Previously, last lecture, we thought of x hat as estimate of x, right? We thought that x hat would simply be our best guess of what x currently is. But it doesn't have to be that. With Leuenberger observer, it is what it is, right? It is best estimate of x. But there is no particular reason why internal state of this dynamic controller should be estimate value of x. As long as the output is correct, we don't care what x hat is, right? So we could have designed a controller in such a way that internal state would have nothing to do with estimation, right? But Leuenberger observer is the idea that you estimate your state exactly like this, and then use it for control purposes. So that's how Leuenberger works. Okay. You can observe the difference between this controller and controller like this, u equals to minus kx. This controller does not have internal state. So you can see it just has a matrix K. So the behavior is much simpler. And it is clear why, right? There are no internal variables. From a programming perspective, this controller would not require you to store any information on your memory. This controller, on the other hand, would require you to have a special variable, x hat in this case, which you have to store in your memory. And you have to update it So you have to somehow design integration law. Like this integration law has to be designed. If it was a discrete controller, then update law would be just addition, basically. But since it is a continuous time controller, you have to use some kind of integration scheme. And you have to update it every control loop. So the control scheme would have to be operable at the frequency of your updates. So like variable step integration is not going to work, right? So that is, from programming perspective, that is a big difference between those two controllers. Dynamic controllers would always have this kind of problem, right? Static controllers never do. Okay. Okay. Now, generic form of a dynamic controller looks something like this. We have our state of the controller, called x dot hat, right? Is equal to ak x hat plus bk y. Y is the input to this controller, right? We have output u, which is equal to ck times x hat plus dk times y. Okay. All of those matrices are controller gains. So now controller has 4 different gain matrices, not 1, 4. Right? And we have to tune those to achieve better performance. So in fact, when we said we use Leuenberger observer here, we automatically tune those matrices by choosing that the state matrix that is in front of x hat, in this case, would be equal to A minus BK minus LC. We just decide that this is what's going to be. Right? By the way, where did it get it from? One more time. Right? A minus BK x hat minus LC x hat. That is what stands in front of x hat. The second matrix would be, in this case, L, right? It stands in front of Y. The third matrix would be, in this case, minus K, what stands in front of A hat on the output. And the last matrix would be 0. Okay. So when we said we are going to choose Leuenberger observer, what we implied is that we use this type of structure for our matrices, right? We would have those 4 matrices, and out of those 4 matrices, we're only going to tune a very specific one component, L. So we only tune L. Everything else we're not tuning, right? Like K is being tuned separately using LQR or pole placement or something. If we want to think of Leuenberger as a control observer pair, well, yeah, then we additionally tune K. So you can see we already import the structure. That is a decision. It doesn't have to be made, but it helps because Leuenberger works really well. Okay. Okay. All right. By the way, here you can notice additional flexibility of this term. This term is called feed-through term. D in this LTI system is always called feed-through term. That's just a standard terminology. So what we can have is U being dependent on the input directly. So if we want our input to directly like algebraically affect our output, we can just have this feed-through term, and that is that. Okay. Okay. Any questions?
Yes, I have a question. Sorry, maybe I missed this, but what actually means tuned? matrices A. Okay, how do we tune them? With LQR or with what? How?
Okay. I understood the question. So, how to tune this controller? That we did not study. In fact, we're not going to study how to tune this controller, because general case like this, there are ways to specifically solve it, right? There exists a tool. Basically, you would look for dynamic output controller, design. There would be a way to do it using techniques related to LMI, linear matrix inequalities, outside of the scope of this course. That's relatively complicated even for graduate course, okay? How to do it in general. But we don't need to do it in general. The whole point of this template is that we need to see how it looks. But instances of this template are easy to tune. So we already know how to work with Leuenberger, right? And that is an instance of this more general template. In just a little bit, we will look in PID, then we'll go look at filters. All of them are instances of the same template. So for this course, we're not going to work on trying to tune the general case, like solve for directly for AK, BK, CK, DK. In fact, almost no one does it. By limiting the choices beforehand, we get much simpler problem that can be easily solved. Solving this general problem is too complicated for what we get from it, usually. Of course, there are works specifically on how to solve this general problem. So yeah, you don't know how to tune because we didn't study it. It's quite complicated, but we'll look at the instances.
Okay, I see. Thank you.
No, thank you for the question. Any other questions? Okay. Let us move on. So we saw all of this, abstraction and so on. Now let's look at concrete instances that are going to be useful. So one of the arguably most famous controllers in general, I would say, together with LQR, is PID. In the older world of engineering, it was maybe almost the only controller that everyone used, PID. In some areas, it is still most likely one and only one controller that people use. Okay. PID is proportional integral derivative controller. The name is greatly chosen, one of the better naming in the whole field, because it has proportional, integral, and derivative terms. Okay. Proportional, integral, derivative. Okay. Has all those three terms. The way it works is you have a coefficient, proportional coefficient, times control error, plus a derivative coefficient times derivative of the control error, plus integral coefficient times integral of the control error. Okay. This works for scalar cases, but of course works for vector case. So output control signal equals to gain, proportional gain. So matrix times error plus derivative gain, matrix, right? Times derivative of the error plus integral gain, matrix times integral of the error. This controller is designed to work for second order systems. So it's not for LTI, not for plants that are described as the first order systems, right? It's for plants that are described as second order systems. What means that there should exist E double dot somewhere. E double dot should exist somewhere. the plant has to contain E double dot. This point might not be completely clear, but essentially, you can think of it this way. If you, inside your controller, you already have a derivative, you have to have a higher derivative in the plant. Controller cannot have as an input derivative which is the highest derivative of your plant. So if your plant is first order system, your controller cannot have any derivatives. If your plant is second order system, let's say like a spring mass damper is described as E double dot plus mu E dot plus K E equal to 0. Well, your controller can have a E dot because E double dot already is in the description of the plant. Right? So that's why it is for second order systems, because we have this term. Yeah. Okay. So this controller is equivalent to linear controllers we studied. So LQR, this U equals to KX. It is equivalent to that, but with one addition. It has integral part, which allows it to compensate for static additive disturbance. Okay. We will not discuss it right now because it's slightly outside of the scope of the course, robustness questions. But basically, you can think of it like this. If your model missed a little bit of the dynamics, let's say the gravity was not computed correctly, and it was not compensated correctly. So your plant, instead of keeping the, let's say your robot has an arm, right? It sits like this. But because the gravity was not compensated correctly, it sags a little bit. So the arm, instead of being like this, it's kind of like this, right? Integral term computes this error. Say, okay, it should be here, but it is here. It computes it, and it integrates it. Over time, this integration accumulates more and more and more and more and more. It is multiplied by this small coefficient ki, and over time, it's going to compensate for this lag, right? It's going to push the arm up until it hits the desired spot, at which point integration stops. I mean, integration goes on, but it is integrating 0, right? Control error is 0. So it integrates 0 here, nothing happens. So that is the idea for PID controller. Except for this term, everything else is exactly the same as what we have seen before. But this term is quite important for practical reasons, because you always have those small error in the models. So people always add those terms to compensate for them, right? Yeah. There is an entire like manuscripts, user manuals on how to tune PID controller. That is a popular subject. So you can easily find, especially in technical literature, descriptions of how to tune PID controller correctly. Like first tune P component, then tune this other component, and so on. Is interesting. You can follow it. In this course, we're not going to study how to do it, but in it's not something very complicated. Essentially, if you trust in this whole thing with compensation, you can just use Ki as a small number. Eventually, it will compensate for the error. Kp and Kd you can design the same way as LQR. That is a good guess if you just want to do it. It's sort of for fun. If you want to do it professionally, it's usually you would have manuals on how to design those coefficients well. All right. Okay. All right. So this PID control. Now we can rewrite it in Laplace variables this way, right? So here is the proportional coefficient, the derivative coefficient, derivatives, remember, becomes variable s, and integral coefficient. Integrals become 1 over s, right? And this is how it relates input to the output, okay, through this relation. We can rewrite it as a transfer function, except this is not a proper transfer function, because for a proper transfer function, the degree of the polynomial upstairs has to be smaller than the degree of the polynomial downstairs. This is not a proper transfer function. The reason it is not proper is because it does not describe ODE. With this guy upstairs, it actually describes exactly what we saw on the previous slide. So what you can describe as differential integral equation. So not ODE, not ODE. Okay. Right. So this is not a proper transfer function. Okay. So from this description, it is not clear if the controller has state or not, right? It's not completely clear. So what we can do is consider it in the state space form, like make it more familiar. In state space form, let's say we assume that our measurements are E and E dot, error and error derivative. You can think of it a position velocity. We measure those P and D. So this is proportional for proportional control. This is for differential control, P and D. Okay. Now we can define a state Z, which is equal to integral over control error. So the integral of a control error we define as a state Z. Is going to be state of our controller. Well, this state, if we differentiate it, what we get is dz dt is equal to E, right? dz dt is equal to E. I mean, strictly speaking, it will be equal to E of t minus E of 0. But let's just for simplicity say dz dt is equal to E, right? But E is our first component of the output, right? Of this y, right? It's input to our controller, it's output to the plant. So it's first component of y. So we simply need to multiply y by I and 0 by this matrix, selector matrix, like I and 0, to get our E, which gives us our dz dt, right? So this is this, right? And that is that. Okay. Now our controller becomes quite simple in description. It is U equals to Ki times Z. So this is K, let me guess be clear. So this is Ki times Z, which is, this is Z, right? Plus Kp times E. Let me again be quite clear on this part. One second. Okay, Kp times Y gives us Kp times E. And here we have Kd times Y giving us Kd times E dot, right? So Y would be, Y is this two-story vector. When you multiply it, will give us Kpe plus Kd E dot. So you can see this second equation is simply a description of the PID controller. Now we can see that it does have a state. The state is Z, right? This state. It is used in the output. It is slightly different from normal plants because it does not have a matrix. So out of 4 matrices, four matrices is, remember, A, B, C, and D, right? Like this matrix is nowhere to be found. It is 0, right? Whereas B matrix here, it is this I0 selector matrix, right? The C matrix is Ki, and finally this D matrix is fit through matrix is KPKD. So here it is. Here it is. Yeah, here it is. And so what you have is PID controller expressed in this form. Now you understand that it is a dynamic controller. The relation between input and output is going to depend on time, which makes sense by how, like, as I described it, it's going to decay this like discrepancy, right? It's going to decay slowly to 0. So yeah, the relations between input and output depend on time. Yeah. If you already tuned KP and KD using some other methods, all you need to do is now to tune KI, right? Which you can attempt to do it simply by closing the loop and seeing that everything is fine. But in practice, this is not like a system. I don't want to say like in practice as if I know how everyone does it in their different plans and so on, but it is not like a systematic practice the way we do it with LQR. For different plans, it will be different. For some plans, it is like KI doesn't need to be very big because it is very precise already. For some other plans, it would be bigger, right? It is a sort of art, you can say. And often enough, when people tune those three coefficients, what they want is to achieve not only stability, but also they want to achieve some certain reaction to harmonic inputs, like Bode plot. They want Bode plot to look a certain way. And often enough, they want to the reaction to certain types of signals, like step response, is when you instantaneously give it input equal to 1. You want the plants to produce less oscillations and less overshoot, etc. All of this is sort of like part of what you want. You want to understand exactly what you want, then you achieve it, and so on. And it can be done by simply how we call it turning the knobs. Like you make Ki smaller, you can make it bigger. Here it's not completely obvious, but when you look at this expression here, let me show you. Right? When you look at this expression, you understand that it's 3 numbers. So you make one number bigger, one number smaller, one number bigger. Your performance changes, and you do it until you get the performance you like. That is a approach that like you see people do. But then, of course, once you figured out how to do exactly what you like, how to achieve good performance on your own terms, like, for example, less overshoot. When your arm, when it stabilizes, it doesn't do this. It kind of does this. Right? When you understand, you can design your own like practices explaining how those components would have to relate to each other. Okay, all right. So what does this knowledge give us? Well, of course, we need to understand that PID would contain a state, so we would need to store something in the on the controller. That should be quite obvious because of the integration here, right? This integration, of course, would imply that we would, like, by doing numeric integration, we would store something. Like, that's how numeric integration works. But it's not artifact of the fact that we do numeric integration. It is the nature of the controller being dynamic, right? That is a difference. That's a difference. Okay. A last remark about PID. Please notice how we used y containing e and e dot, and we fed them through here. Okay. It's tempting to try to use PID on normal LTI systems, but or to try to only pass e as input. But just keep in mind that this e dot is one of the states of the system. Like for the second order system, the state is the position and velocity, right? Not just the position. Velocity is also one of the states. States, you remember when we defined them in the first lecture, is the variables that define the current position of the system. They are sufficient to predict, like if you know current state, you can predict all future actions of the system. You need to know current velocity to predict how the system will go forward, right? It goes back to Cauchy problem. For second order system, you need to know initial conditions related to position and related to velocities. Right? I mean, of course, you can do like boundary conditions and so on, which would replace those, but yeah, let's not go into too deeply there. So states contain position and velocity, and we pass them through here, and that's how we get our U output. Okay. Now, last example for today is filters. That is going to be something that is essentially has the same form as what we saw previously, but it won't, like in terms of description, it won't look anything like a controller. So let us just start with an example. So let's say you have the system, scalar system, x dot equals to ax plus bu, and the output of the system is y equals to cx plus a disturbance. So this disturbance is itself a signal. It is d times sine on wt, right? Okay. D times sine wt, where w is high frequency, a very high frequency. When I say very high, I mean it is much higher than what we hope to see in terms of behavior of x. Like if we exclude this term, then x would be much slower in how it behaves compared to this frequency, right? Okay. So if, for example, if you want a concrete example, what's going on here? Imagine there's a motor that rotates let's say it's a pick and place operation, like goes pick, place, pick, place. This motor operates at the like the motions are at the frequency of 1 hertz, right? One pick and place a second, right? 1, 2, 1, 2, 1, 2. This kind of frequency. But in the measurement, and remember, this is a measurement. This part is a measurement, right? This equation here describes the measurement. In this measurement part, we have sensor noise, right? Our noise adds let's say 10 kilohertz kind of noise to the measurements. So whereas we expect to see only 1 hertz frequency updates on x, right? What I mean by that is we expect x to behave like a sinusoid, roughly speaking, with the frequency 1 kilohertz. It is a sinusoid with a small kind of like this tremor, right? This tremor is 10 kilohertz. Okay. So essentially, we just want to get rid of this guy. We want to get rid of this high frequency component. Like what we want to do is cancel it. Without it, we can just get our control equals to ky, and we'll be happy. Because in this case, y is equal to cx. It is the same number of dimensions. No problems. We should be able to make it stable. But this high frequency, we don't want to get it into our controller. So how do we do it? Well, the way we can do it is to pass the measurements y through a system that would attenuate high frequency components. Attenuate means to squish them down, right? High frequency components, let's say they were amplitude 0.1. We want to make them amplitude 0.001, right? We want to squish them, make them small, insignificant. Okay. System like this is called low pass filter. Low pass filter because signals with low frequencies pass through, high frequencies get attenuated. Okay, so essentially, for example, we can do it this way. Let me elaborate what we do here. So this system on the top receives input y from here, right? It affects z dot, right, in this manner. And then z dot is being multiplied by controller gain k and being passed out, right? So z, you can think of it as a filtered version of y, right? And u is your control output, your control signal. So somehow this system is supposed to filter out this noise. Let's see how it's done. Well, this filter, that z dot equals to minus z plus y, has a Laplace form here. How do we get this Laplace form? Let's remember. It is z times s equal to minus z plus y. That is like we replace the derivatives with s. Then we concentrate all the z parts on the left-hand side. We get s plus 1 times z equal to y, right? And then we divide both sides by s plus 1. And we get our 1 over s plus 1. That is z equals to 1 over s plus 1 times y. Now, if you remember the lecture on Bode plots, in that lecture, we studied how to understand the frequency response of the system, how it attenuates or increases the input frequencies, so amplitudes of the signals on different frequencies, right? How it's done? Well, first step, I will just remind you, first step is replace S with omega j, right? Omega j, where omega is your frequency, j is imaginary number. Okay, so you would get, after the first step, you would get 1 over omega j plus 1, okay, as your transfer function. Step number 2, compute absolute value of the resulting transfer function. Absolute value of the resulting transfer function, that is your, and this is basically your attenuation. How do we compute absolute value of 1 divided by omega j plus 1? We multiply both sides by conjugate pair to omega j plus 1. So you would get something like 1 minus omega j in the upstairs, right? And downstairs you would get omega squared. Let me write like this. Omega squared 1 minus omega squared, something like this, right? 1 minus omega squared. Yeah. Then what you do next is you that is the first step, right? Sorry, that is just to make sure that you don't have J downstairs. And then what does it mean to have absolute value? Well, you get a real part. Real part here is this guy divided by this plus squared plus imaginary part divided by this squared. Right. And you take square root. What you would find is that you would have this expression after you finish this calculation. All of this you can find almost exact same example you can see in the lecture on Bode plots. So just in case you can refresh your memory by going there. Okay. So what we have is this expression giving you how much the system attenuates your signal. Right? Okay. Now, how much does it attenuate? Let's see. Well, if omega is small, let's say almost zero, if it is close to zero, then this whole transfer function becomes 1. 1 over square root of 1 is 1, right? So on the low frequencies, it doesn't do anything. Now, what if omega is a very big number? Well, then this is almost 0. So signal goes away completely. And we said that for our task, the W is a high frequency. So it is going to go almost to 0. So D will be divided by let's see what's going to exactly to happen to the signal. So after it passes through this filter, it is going to be multiplied. The D is going to be multiplied by this 1 over square root of W squared plus 1, right? So if W was like, let's say 10 kilohertz, that is 100 million. Of course, we have to transfer from hertz to radians per second, but it's not going to save the signal. So the signal is going to go down. It's going to be attenuated to almost nothing. Yeah. I mean, sorry, here I made a classical mistake. So 10 kilohertz squared, 100 million. Square root back to 10,000. Sorry. So this signal is going to be basically 10,000 times smaller. Again, remember to transfer to radians per second. So it would be, roughly speaking, 10,000 times smaller. Okay. Okay. So you can see that this is going to solve this problem. Like our signal noise, if it was anything noticeable, it's going to almost disappear into oblivion. We're not going to see it after it passes through this filter. That's very practical. And by the way, this can be done with analog components. We don't even need to do it on a computer. We can just put a condenser and a resistor there and build what we call RS loop. I'm not going to stop to explain how electrodynamics works for this loop, but basically it can be done in analog way. And often enough, your primitive electronics would have this type of loops built in. So it's quite typical. It's quite typical. But of course, we can do it also on a computer. So you can see what we have here is yet another dynamic controller. This time it has nothing to do with stability, this whole thing. Stability will be designed specifically by choice of K. But the filter, this ability to attenuate frequencies, would be dependent on what we put in front of Z, like basically the eigenvalue of the system. If the eigenvalue would be much smaller, the attenuation will be, different, right? You can figure out how it's going to influence attenuation by going through our derivations, right? You can try to see how Bode plot changes if we choose different value here. But yeah. So somehow we combined here filter and controller, and we still get what we would call a dynamic controller. There is no rules that we have to specifically combine Leuenberger observer and controller to get something workable. Like here, like this guy doesn't have anything to do with this system in terms of its form, but it does a useful function. It attenuates the output signal. In fact, this type of performance metrics is often almost more important than the like optimality in the sense of linear quadratic regulator. We want to see how the system reacts to disturbances that come from outside, such as this one, right? So that was another example. That was another example. All right. So just to conclude what we saw today, we saw that we have a whole realm of controllers, right? We have controllers in this form, just a combination of very, honest and simple observation, like estimation methods, like Leuenberg observer, plus a completely normal controller, right? And that is a dynamical system, right? It behaves slightly differently from just normal control. We saw that we can have linear proportional integral derivative controller, right? It tries to achieve something we call robustness, right? Compensate for some errors in the models. Also behaves in a similar way. We saw that we could do filters, which specifically designed for getting rid of external outputs of high frequencies. Also goes down to the same general structure. This structure is very rich. You can do a whole lot more of it. For example, you could design a system which would delete I'm using simplified terminology, forgive me, like delete additional elements like this. Let's say you have input, which is static, just a static input, but you don't know what it is. Like you absolutely don't know what it is. You can design again a controller in this form, and that will be called disturbance observer. I'm not going to go into details how it's done, but just saying, another one thing you can do with this form. Yet another thing is, if you don't know A for sure, you can also design a control in this form, and it would achieve the same performance. Yeah, so it is a rich field of controllers. Yeah. Often enough, when you are going to encounter a real problem, you would have to ask yourself what type of controller you're going to use. And this question should not be limited to how to get K for the controller U equals to Kx, right? That if you want a simple conclusion to this lecture, that is a conclusion. When you encounter a real problem, you shouldn't start by asking yourself, how do you get K in the, all right, let me just write it down. How do I get K in the Kx controller to solve this problem? That shouldn't be the first thing that you ask. First thing should be, Okay, what are my options? Do I use static controller like this, or controller with a state, like the ones that we considered? And the controllers with a state, then you look at your possibilities. What we saw today: filters, observers, PID, and so on. There are other possibilities, of course. That's just ones. All right. With that, I want to conclude. If I'll stop the recording, and then if we have questions, we can discuss.